race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. The Walkie-Talkie, the communication essential born from the battlefield. Ultrasound, seeking submarines to scanning the human body. Patient simulators, training astronauts for emergencies in space. We reveal the amazing science and manufacture behind these wicked inventions. Allowing us to communicate with each other and used by all sections of society, from the emergency services to children at play. The technology behind the handheld receiver was actually developed during World War II.
The handheld radio, and what became later known as a walkie-talkie, was developed during the Second World War, and it became a really useful tool for communicating between troops, between regiments, so that people could give advance warning of things happening. It was another way of using a radio, but just doing it in a more portable, immediate way.
They required the user to have a large backpack, mainly containing radio frequency sending and receiving equipment, and a battery, because battery technology was not as advanced as it is today with lithium-ion batteries and rechargeable batteries. So it wasn't a handheld device.
Walkie-talkies work by using radio waves to wirelessly transmit and receive speech over a shared frequency band. Classed as two-way radio, a walkie-talkie can only transmit or receive at any given time by using a push-to-talk button which is pressed when the user wishes to speak that turns the receiver into a transmitter. And once released, the walkie-talkie reverts to receiving. As the name suggests, a two-way radio works like the radio you listen to at home, but its small antenna size and power output means it has a limited range.
Radios are designed to receive frequencies that are imparted over a very long range. Walkie-talkies, by contrast, are designed to receive radio frequencies over a limited series of ranges, and then what they're designed to do is also be able to transmit back on those same frequencies. So the benefit of a walkie-talkie is for person-to-person communication, but its range is limited. Even with a repeater, you're talking about 2 to 3 kilometers, maybe a few more. A normal radio can pick up radio frequencies broadcast to it over hundreds of kilometers if AM, or under 100 kilometers with its FM.
The walkie-talkie, developed in World War II and still going strong today. It's truly a wicked invention. Based near Manila in the Philippines, Entel was established in 1995 and have grown to be a leading manufacturer of commercial-grade two-way radios in the global market. Consisting of over 4,000 different parts, the production of the two-way radio is a long and detailed process, which all starts here at the kitting department. Each component is checked by hand under Entel's strict quality standards before they can be moved into kitting boxes. Entel's sophisticated real-time tracking and inventory system provides the exact location of every part that comprises the build of these radios.
To ensure this consistent level of performance at every stage of the manufacturing process, the various components of the radio go through stringent checks and verification. More than 500,000 lines of code are loaded by our automated test equipment. There are about 39 processes that make up the parts used on the digital radio, and developing and manufacturing the materials is definitely an extensive process.
Production starts with electrical circuits. Each component is mounted directly onto the printed circuit boards, also known as PCBs, by precision pick-and-place machines. They then go through a series of heat zones, where the components bond together with the board. The boards are then inspected by multiple forms of visual inspection, be it by hand, microscope and X-ray, to make sure that even the smallest component is cleared before moving on. Next it's on to sub-assembly, where lines of workers with individual roles now add the mechanical and electronic parts to the PCBs. These are dedicated lines that comprise of teams processing the electrical or mechanical assemblies. This helps with productivity and efficiency, as one by one the lines can create the PCB for the mechanical keypads, frame and top covers, while the electrical assembly builds switches, encoders, mics and speakers. The intention is that the lines work together as a unit or one-piece flow. This way increases productivity. The new circuit boards are placed onto a fabricated metal frame, which will become the main body of the radio. They are secured and then carefully screwed together. New high-impact polymer cases arrive on the production line. Some branding will be added before inserting the PCB and all external mechanical parts, such as the knobs.
Users of handheld radio are many and varied, and include clients in industries such as blue light, armed forces, petrochemical, utilities, shipping, heavy industry, leisure and retail. Hand portables available today use extremely power-efficient silicon electronics. This enables the use of compact and lightweight batteries.
One of Intel's technology strengths is built around its own custom-designed and unique automated testing stations that ensure each and every radio is fully compliant to its test specifications. Before full assembly of the radio, each board's serial number is scanned, calibration data applied and the board tested. The board serial number, together with its test results, are then automatically uploaded to the manufacturing database.
There are many advantages of handheld radios. Handheld radios don't rely on third-party infrastructures to provide coverage and therefore can be deployed anywhere. They provide instantaneous group communications at the press of a button, which eliminates the need to set up a conference call or wait for the phone to ring and then be answered. This form of instantaneous group communication is essential to users such as the UK Fire Service, one of the many emergency, armed and government services worldwide that use Intel radios for critical communications. Because they don't rely on third-party hardware, handheld radios don't have the airtime, call or data fees associated as do mobile phones. No matter how many calls are made, text messages sent or data used, when using handheld radios you have a fixed, low-cost system.
After a series of automatic tests, it is now time for final assembly of the radio. Intel produces its own batteries and accessories. Here we see two high-capacity lithium-ion cells being verified and assembled into a battery pack using a spot welding machine. Once the main body has been assembled, it is time for final testing of the completed radio. Intel's automated test station identifies the radio model being built, then downloads the test script from the production database. The radio is connected inside the test unit and the system automatically picks data from pre-assembled tests, tunes the radio and adds all necessary firmware. The results are instantly shown on a monitor so the operator can view its performance. Once passed, a unique label is printed which will go with the radio to the packaging area. The special label gives all the information needed so the batteries and any accessories can be placed into its presentation box, sealed and sent out for shipment. The walkie-talkie, truly a wicked invention. When we think of ultrasound technology, we immediately picture a pregnant mother being scanned to see how the baby is developing. But this amazing technique was actually originally developed to fight the submarine threat to Britain during both World Wars.
Submarines posed a huge threat in both the First World War and the Second World War, not just to our own warships, but more importantly to the merchant shipping. So it was certainly realised that countering the submarine was vital, and the first part of that was means of detecting. Initially started off called ASDIC, and really it was the use of sound waves, or what Sonar, as it became later called, to detect large underwater metal objects like submarines in the wartime.
As an object moves through water, it vibrates and creates sound pressure waves that alternatively compress and decompress the water molecules in the sea as the sound wave travels through the water. These waves radiate away from the object like ripples on the surface of a pond, and can even bounce off nearby objects and reflect back to the original source. Early, passive sonar devices just listened for these sound waves, but scientists soon developed active sonar, where a ship could transmit an acoustic signal into the sea, and if a submarine was in its path, the sound would bounce off the submarine and return an echo to the sonar device. By determining the time between the emission of the sound signal and its reception, the device could determine the range and orientation of the object, and the ship could then attack. Not surprisingly, this technology has found other naval applications in peacetime.
It's become used not just to look for submarines, but a whole variety of other purposes. It's actually very good, for example, of finding fish. And now most modern fishing fleets all have sonars in their vessels to detect large fishing shoals for them to be able to go after. It's also very good for bottom mapping, a contour mapping, looking at the seabed, which we didn't have before.
In sonar technology, ultrasound is used. These are sound waves with a really high frequency, which exceeds our own hearing limit of 20 kHz. Even though humans cannot hear these sounds, animals such as bats and dolphins can, and use them to detect their prey. What makes ultrasound so useful for applications like sonar is the fact that the higher the wave frequency, the shorter the distance between the peak of each wave, and the shorter the wave means the better it will reflect from an object. And this phenomenon has led to the ultrasound scans that we are so familiar with today.
So sound waves get projected into the body and they are reflected back by different tissues and they produce different patterns. When they come back to the probe, it picks up those reflected sound waves and then a computer program processes it to produce images. These have developed even further, where you now can produce 3D images of the baby in the womb.
But there is a reason our bodies are so suitable to ultrasound examination that has led to many medical uses for this technology.
Ultrasound is used in many different ways. We know more about the prenatal uses of them, but it can also be used for investigating other gynecological problems, but also lumps and bumps anywhere on your body. By looking at the different properties of different tissues, it can identify a fluid fill cyst between a fatty lump on a body. Also, it can be used in looking at the circulation and blood flow, and it's ideal for the human body because it contains a lot of water, and so there's a very reflective process that can go on to build up images using ultrasound. There is no dangerous substances that are being used, just sound waves which doesn't damage any tissue on a longer term basis or repeated exposures.
Developed to combat submarines, but now used to investigate our bodies and see babies for the first time. Ultrasound, truly a wicked invention. Our intrepid tester has been inspired by the story of the development of ultrasound to try and create his own mini submarine made out of a few food cupboard essentials. What you will need: a vase of water, a pair of scissors, screwdrivers, some drawing pins, some plastic packaging foam, a pencil, a carrot, a knife, and some baking powder, not to be confused with baking soda. To begin, take your carrot and cut it down into a rectangle that is approximately 6 centimeters long and 2 centimeters square at the ends. Check your carrot's buoyancy. If you place it in the water and it sinks too quickly, shave off more of the carrot until it slowly sinks to the bottom. Once you are happy with your carrot's performance, take the screwdriver and carefully create 3 holes on the underside. The hole should only be about half the depth of the vegetable side, and take care not to pierce the top. Carefully open out the edge of the middle hole to create a beveled finish. This will become our flotation chamber. To create our veggie subs coning tower, cut a small piece of the packaging foam and use a drawing pin to fix it to the middle of the top side of the carrot. You can be generous with the amount of foam, as this will be trimmed to fine-tune our submarine's buoyancy later. Now take 4 more drawing pins and fix them to the corners of the bottom of the sub to create mini landing legs for our submarine. Next, let's fine-tune our sub's buoyancy. Drop your veggie submarine gently into the water. It should float with the coning tower just breaking the surface. But we want the sub to very gently sink to the bottom of the vase, so gradually trim the foam from the coning tower and keep testing and repeating until you get the desired results. Take the baking powder and carefully fill the central hole of the sub, taking time to firmly ram the powder in with the end of the pencil. it is now time for our first dive. Gently let the submarine fall to the bottom of the vase. After a few moments, you should see our orangey explorer slowly float to the surface. And there she goes! And the science? The baking powder reacts with the water and produces a carbon dioxide bubble of air, which forms in the flotation chamber and provides just enough buoyancy for our little sub to rise. So, there you go, your very own veggie submarine. When training for medical emergencies, doctors, medics and first aiders need to be able to practice safely without causing harm to patients, whilst also allowing for error as they learn. In order to do this, patient simulators are used. We may be familiar with the mannequins used in first aid training, but patient simulators today can mimic far more medical traumas and continue to be developed to offer as real a simulation as possible in a wide range of medical emergencies.
Patient simulators are used in lots of different ways to help training for medical staff. Very much like a pilot might use a simulator to help practice different manoeuvres or emergencies, we can use them in the medical field as well. So for instance, we might use them to help practice in examinations which are too uncomfortable for a patient to have done repeatedly to them, or perhaps aren't safe for a doctor to train on them. So it's a good way of practicing so that when you meet those situations that you are as well trained as you can be and the patient is safe.
So, how important are patient simulators in the training of medics?
They're very important. We use them a lot. We have models that we practice on. They also have scenarios which you can practice. So for the mannequin, you'll have safety scenarios where you practice protocols on resuscitation. We also then use simulators on a slightly larger scale, perhaps for a major incident. So a hospital will practice how they run the hospital given a major incident. So that may be personnel communications, as well as using mannequins to replicate patients and the different clinical scenarios they may present with given that major incident.
Patient simulators have proved particularly useful for NASA, allowing them to develop new techniques of medical care specifically designed for zero-gravity environments, where normal procedures may not work, and where it is impossible for medical assistance to arrive in emergencies. As well as in space, patient simulators have become indispensable in the training of military medics. In battle, a medic must act fast, and most importantly, they must remain calm. By training on a patient simulator, the medic can improve their response time and build confidence before going out into the field. Today, patient simulators can mimic extremely complex medical conditions and emergencies. The use of hydraulics, magnetic fluids and wireless technology mean that they can respond in ways that closely resemble real-world situations.
So you can suddenly have a patient simulator that starts to mimic the spasms much more accurately, because you can have liquids that are in a certain position spasm and flow and actually mimic the muscles moving about, so a patient could be thrashing while you're trying to help save their life, which is actually quite common. So you may want to have the internal organs working as they could be, controlled by a computer, but they'll be simulated such so that you know what to feel and what to expect when you're in an emergency.
Patient simulators have undoubtedly saved lives, as they allow a chance for medical professionals to improve their skills in a risk-free environment, meaning that when an emergency presents itself, they're much better prepared to deal with it. CAE is a global leader in providing comprehensive training solutions based on world-leading simulation technology. CAE delivers integrated training services to civil aviation, defence forces and healthcare.
CAE Healthcare is the most comprehensive medical simulation company in the world. The benefit of training with a patient simulator is that these practitioners, these doctors, nurses, and medics can practice in a risk-free environment before they even touch a patient.
The METI-MAN is a high-fidelity, wireless patient simulator that is used to train physicians, nurses, paramedics, military medics, and interdisciplinary teams to respond to medical emergencies. A medical robot that blinks, breathes, and bleeds, METI-MAN is produced by human hands from 880 parts. In the production of the METI-MAN, the team assembles 13 kits of parts relating to METI-MAN's head, limbs, and torso.
The benefits we have by building the METI-MAN in the various steps is it reduces our lead times. By breaking up the simulator into different units, we actually can integrate our testing into the assembly stage and not wait until the final ATP testing. So those are big advantages we have by doing that.
A team of 1 to 2 people build Mediman's torso tray, consisting of his convulsion motor, pneumatic valves and internal plumbing for simulated body fluids in about 2 to 3 hours. While the first team is building the torso tray, another team spends 2 to 3 hours building Mediman's wiring harness, which delivers power to all of Mediman's moving parts and internal software, and then performs the final assembly of Mediman's torso tray into the torso skin. After this, the right arm, right leg, left arm and left leg are then built. They contain the pumps for his fluid secretions and bleeding ports, pneumatic air pumps for his breathing and for the pulses on his neck, arms, legs and feet. One individual builds his rib cage, which contains his lungs. The head assembly is then built and tested, which contain his airway and his reactive eyes, with pupils that contract or dilate based on his medical condition. Before attaching the head, the technician tests his eyes as well as his airway, which can be open or constricted based on his medical condition. They test the laryngospasm feature, which simulates the vocal cords blocking the passage of air due to a medical condition. Mediman undergoes 2 to 3 hours of testing by a quality assurance professional who operates him with the software interface to test his eyes, breathing, pulses and more.
Our Mediman human patient simulator, one of the major features that differentiated itself on the market was the fact that it is a wireless simulator. You no longer have a tether connecting actually to the unit, so it's a wireless simulator that you can connect. So for the nurses, everyone to use, the unit is actually more maneuverable. You don't have all those wires connecting to it, so it's a lot more easier to use.
The airway is tested with a laryngoscope that is inserted into his throat with a camera at the end, which allows the quality assurance professional to see his airway responses. A team of 2 people then spends an hour covering his body with skin made of plasticized PVC on the body and reinforced silicone over his face. The silicone is softer and more pliable to go over moving parts like his jaw, while the plasticized PVC is more rugged for movement and rough handling. Once he has his skin, Mediman returns for a final round of testing, and the team moves his arms and legs and other parts to make sure fittings stay connected. Now that Mediman is complete and has passed all tests, he is ready to be put to work and able to provide potentially life-saving training.
Some of the features that make Mediman so unique when compared to the low-end CPR mannequins that we grew up with is that he's what's called physiologically based. And what that means is, if he's given a specific medical condition, let's say for instance a massive medical trauma where he's bleeding profusely, all his vital signs will adjust accordingly. So his blood pressure will start to drop, his heart rate will start to go up, his breathing will become more and more rapid, and eventually, if the right medical interventions aren't taken, Mediman will die.
The patient simulator. Truly a wicked invention. So there you have it. A dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. The walkie-talkie, ultrasound and patient simulators, all wicked inventions.